All right, our talk today is by Yuri Sulyma, who will be telling us about slice 2 periodicity and ROG graded homotopy.
All right, thanks for the introduction and the invitation to speak. I'm really excited to tell you about this. So the context of what I'll be telling you about today is, oops, oh, and forgive the transitions. So a few years ago, Botmore and Schulze did some really exciting work connecting topological Hausdorff homology and equivariant homotopy to arithmetic geometry. And so the key calculation that went into their paper was studying the Postnikov filtration on THH of perfectoid rings. The result being that it's two periodic or two polynomial. And this generalizes and ultimately reduces to Bachstedt periodicity when R is FP. And if you don't like the word perfectoid, you can think of R as being FP throughout. So then Mike Hill asked, what would happen if we replace the Postnikov filtration by the slice filtration coming from equivariant stable homotopy theory? So this is a generalization of the Postnikov filtration that's different from the equivariant Postnikov T structure that mixes in more of the representation theory and is somewhat more natural. So to understand the results, that's what I looked into, we can restate the BMS result as saying that about the Whitehead, a statement about the Whitehead tower of THH, that the 2n connective cover of THH is just the 2n suspension of THH, and then the map is just given by sigma to the n. So the slice filtration turns out to be given by the slice 2n cover is given now by some ROG graded suspension of THH. I'll tell you what that representation is in a moment. And then the slices of THH are certain ROG graded suspensions of certain Mackey functors. So here, this is the Mackey functor of Witt vectors. And this means you make all the restriction maps above Cn injective, where by Cn I really mean C to the Cp to the Vpn. So in previous talks that I've given on this, I've spent half the talk waxing philosophical about Q analogs. So if you'd like to hear about that, the conceptual side of the story and the connections to arithmetic geometry, you can watch that talk or just read the paper. In this talk, since it's the eCHT seminar, instead I'm going to talk more about how to do the actual computations and talk more about the equivariant homotopy side, which is sort of swept to the rug in the other one, swept under the rug. Okay, so so this representation n lambda, I will tell you later what it is as a circle representation, but it has the property that if we restrict it from a circle representation to a Cn representation, that's the same as just inducing the trivial representation up to Cn. So in other words, the complex regular representation of n lambda, or sorry, the complex regular representation of Cn. And therefore, if you take the representation sphere for S, this bracket n lambda, as a Cn spectrum, that is the norm of S2 from a trivial spectrum to a Cn spectrum. So as a slogan, you can say the Postnikov filtration is generated by the powers of the Bachstedt generator, whereas the slice filtration is generated by the norms of the Bachstedt generator. This is a very nice slogan. It's a bit of a, it only really makes sense like after you restrict to a subgroup and the ends here have to be the same. So I'd very much like to have a description of this, a norm-like description of this as a T representation. But as a slogan, this is pretty good. Also, this is a theorem of Almond studying the slice filtration on equivariant complex K theory. And these representations show up there as well. So when G is a finite cyclic group, the 2n slice cover of KUG is given by this same suspension of the then connective cover of KUG. So this is good evidence that this is a good notion of slice 2 periodic, at least for CK spectra when G is finite cyclic. And so if you have some G spectrum where G is finite cyclic and the underlying is 2 periodic, this should be your first guess for the slice filtration. So let me start by talking about like what the slice filtration is. So this is modeled on the slice filtration from motivic homotopy theory. It was originally introduced by Duggar in the case where G is C2, and then it was generalized to G being a finite group by Hill, Hopkins, Ravenel. This was the key technical breakthrough in their solution of the Equivariant invariant 1 problem. This gives sort of a very efficient filtration for G spectra. So its motivation for this, let me ask, how could we define the connectivity of a G space? Well, a complete answer would be to look at, so view this as a function from conjugacy classes of subgroups of G to Z, or I guess in this case N, since we're talking about spaces, that records the connectivity of all of the fixed points. But what if we just wanted a single integer summing up all this information? So the sort of Postnikov or answer to this is to say that X is X is N connective if and only if all of the subgroup or all of the fixed points spaces are N connective. So you're defining the connectivity as like the minimum of the connectivity over all the subgroups. And this works just fine. You can get like a good theory out of this, but it's not so natural geometrically. So for example, let's consider this usual cellular filtration of Cp to the n, which has associated graded even dimensional spheres. Now, if we think though about the complex conjugation action on Cpn, and then we take the fixed points, then we get the cell structure for Rpn. And then here, the associated graded is going to be, give us spheres in all dimensions. So actually, so really if we think about what these spheres were, this S2 is actually an S row, where rho is the regular representation of C2. So rho is equal to 1 plus sigma, where 1 is the one-dimensional trivial representation, and sigma, in this case, is the sign representation. And the sign representation goes away when you take C2. So here we've got like what would normally be a 2-cell for RP2, but we're attaching it at the same time as something that is topologically a 4-sphere or a 4-cell. So we should expect that, if you have an action by a group, we would expect the fixed points to cut down on the connectivity by roughly the order, or basically divide the connectivity by the order of the group. So if we allow these S rows or these representation spheres as our our associated graded, then we'll be able to run cell structures on all of the different subgroups simultaneously and compatibly. So it's more natural to allow this guy, even though it's an S2, to be considered for connective. Okay, so that's some motivation. So the actual definition is, so let G be a finite group. We define the slice n cells to be, we take, like one way to say it is you take Sk, where k divides the order of n, then you norm that up to an H spectrum, so that now you have k times the regular representation of H, and then you induce that up to a G spectrum. Then we define something to be slice n connective if it's in the localizing subcategory generated by these things. And then X is slice truncated if n+1 connective spectra don't map into it. So then we get a cofiber sequence where this is the nth slice cover, this is the n-1st slice truncation, and then the n slice is apply each of those operations in either order. And so we're dealing with the group S1, or really I'm only going to be dealing with the p-typical subgroups. We'll interpret this just so that it restricts to the slice filtration on all of the finite subgroups. So Hill-Yarnall gave a more convenient characterization of slice n connectivity, which is in line with that sort of dividing out by the order of the group I just mentioned. So a spectrum is slice n connective if and only if the h geometric fixed points are h over n over the size of h connective for all subgroups. So this is a very geometric filtration, and roughly it should be accessible anytime you have control over the geometric fixed points of your spectrum. And so now we have the slogan that the slice filtration is sort of taking the Postnikov filtrations over all the subgroups and then stretching them out by the order of that subgroup and then weaving them all together. If we want to access the slice filtration, so this is, in our case, X is slice n connective if and only if this for all powers of p. So we say X is a slice sphere if all of its geometric fixed points are wedges of spheres. So this is what you would want if you want on each subgroup to get like a cellular filtration. Now, unfortunately, not all representation spheres are slice spheres, but in nice cases, they are. So in our case, we'll be able to just work with representation spheres. So Dylan Wilson gives a recipe to compute, a general formula to compute the slices of a spectrum using these slice spheres, and also identifies the category of n slices with something algebraic. So unlike a T structure, the category of n slices and the category of n-1 slices are generally not going to be equivalent. So the slice filtration does not come from a T structure. But yeah, so in our situation, we'll basically be able to just guess the answer and then prove that it is, in fact, the correct answer. So we'll use a recognition criterion, just saying if you have a bunch of stuff fitting together into your spectrum, each thing is appropriately connective, and then the co-fibers are slices, so they're n truncated and n connective, then that has to be the slice tower. So first, let's go over the representation theory of the group we're working with, which is the circle group. So the complex representation ring of the circle is given by z lambda plus or minus. So lambda is just the natural complex representation of the circle. And then if we use the ring structure of RUT, then lambda to the power of I is still one-dimensional complex representation, but now a complex number in the circle acts by its ith power. So it's sort of interesting that for the purposes of grading homology and cohomology theories, the multiplication on this representation ring is irrelevant, but it turns out to be convenient for keeping track of induced representations. So to see that, I'll define n lambda to be the lambda analog of n by just this sum, lambda 0 plus lambda 1 plus dot 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 plus lambda n minus 1. So here again, lambda 0 is a trivial complex representation. So this is summing in particular over all of the irreps of Cn. And so we see that as a Cn representation, it's just the regular representation, or the induced representation, as I said. I'll also set lambda times n lambda to be the sum from lambda 1 up to lambda n. And then, so then this is the complex regular representation of lambda n plus 1 minus the trivial complex representation. So this is, this restricts to the reduced regular complex representation of Cn plus 1. So that's another sort of interesting relation that you can only see multiplicatively. Now we're going to be working in the p-local context, and p-locally, these representation spheres end up being homotopy equivalent if and only if the p-adic valuations of the exponents are the same. So we'll reindex and write lambda sub I to be lambda to the p to the I. So now lambda sub 0 is lambda. Lambda sub infinity is the trivial complex representation. And so I'll usually write lambda infinity instead of 2. And then 1 will mean, if I write it, will mean a trivial real representation. So we'll define dr of alpha to mean the complex dimension of the CPR fixed points of a virtual representation. This is what we're interested in. So explicitly, if you write out alpha in this decomposition into these irreducibles, then p-typical irreducibles, then dr alpha is just going to be throwing away the things before r, and then summing up all the coefficients. And this includes the trivial representation. And then you can recover. So it turns out to be a lot more convenient to index representations, which are scribe representations, via this sequence of dimensions. So a little bit, maybe kind of like motivic grading, as opposed to breaking them up into this irrep decomposition. And so you can recover the coefficients in the irreducible decomposition from the dimension sequence like this. Okay, so we're interested in the p-typical decomposition of those representations. Now I claim that these are given by, so the dr of lambda n lambda is floor n over p to the r, and dr of bracket n lambda is ceiling p to n over p to the r. And this is supposed to be a picture of this. So in doing this p-typical decomposition, right, we're looking at, we're taking lambda to some power, and then just looking at the p-adic valuation of that power. So if I had, say, lambda 5 lambda, then I would be summing up lambda 1 to the plus lambda to the 2 plus lambda to the 3, and so on. So this floor expression, this is counting, if we go like that many bars, this is counting the number of bars that high up, the number of bars in the rth row. If we say the 0th row, first row, second row, and then we get the count for this one, where we include the trivial representation just by shifting this, because the trivial representation will always contribute a fixed point. So a useful identity to remember when working with these is floor of n over p to the r minus 1, or ceiling is floor of n minus 1 over p to the r. And so in some way, the relationship between the complex regular representation of Cn and the complex reduced regular representation of Cn plus 1 is like a categorification or a lift of just this arithmetic identity. So this picture I've made for illustrating the p-typical decomposition appears in several other contexts. And there's, in fact, a reason, a mathematical reason for choosing the colors of the rainbow to color it. So I'll just briefly mention some connections. So we now have two instances of the expression floor n over p to the r, or ceiling n over p to the r, closely related things. So it appeared in our definition, or in the Hill-Yarnall characterization of the slice filtration, and now it shows up in representation theory as the p-typical decomposition of regular representations. This expression also comes up in Legendre's formula for the p-adic valuation of a factorial, as well as a Q deformation of that problem that comes up in arithmetic geometry. So that is talked about in my paper. Some other connections which I'm currently investigating are, it also shows up in when you're taking the p-typical decomposition of big width vectors into p-typical width vectors, as well as in expressions for the K theory of truncated polynomial algebras, or especially the Hodge filtration on its derived crystalline cohomology. So now I want to talk about, I'm going to switch to writing as part of the dense, talk about how to do computations, equivariant computations with those spheres. I have to left myself room to write, but I might need to see if I can do this, and if not, I'll use the Zoom whiteboard. No, not that one. Okay. So we have very convenient cell structures for these representation spheres S lambda j. Namely, we start out with an S0, just acting trivially. Then we add these spokes, the bird cage, and then we add in a 2-cell. So let's say we've got M is a Mackey functor for CP. So I'll write this as a Lewis diagram like so. So we've got some M1 module, some M0 module, restriction, transfer. And we'd like to know, let's say, the homology of S. This is going to be S lambda 0 with coefficients in this Mackey functor M. So here we've got our associated graded is S0, S1 smash CP over E plus, and smash S2 or S2 smash CP over E plus. So when we smash with CP over E plus, that's the same as restricting down to a trivial subgroup and then inducing back up. So this homology will be the homology of the chain complex. So here, like the underlying of this is M0 CP because we've induced, and then the fixed points of that is M0. And then here we've got the original Mackey functor that we were working with. So these are like diagonal and codiagonal. Then here, this is 1 minus gamma, 1 minus gamma. Here we have the trace, restriction, trace. And then here you're going to have this map again. And then these are in degrees 2, 1, and 0. Now, remember, if M is if we call N is just a group with an action of G, which I should write BG, then we can get a Mackey functor out of this in 2 different ways. We could look at the orbits Mackey functor, which will have M, so we'll have M CP, the orbits here, and then this will be given by the trace, and then this will be given by the quotient map. Or we could have the fixed point Mackey functor of N. Where now this is the trace and this is the inclusion. This is quotient, include. But we know that both of these categories, the category of orbit Mackey functors or the category of fixed point Mackey functors inside the category of Mackey functors, both of these are abstractly isomorphic to the category of just G modules. Okay, so let's look at this homology. We want to evaluate this. So let's suppose that that the trace map induces an isomorphism from M0 orbits to M1. So here we're going to have the kernel of the trace, and then we're going to mod out by the image of 1 minus gamma, which is going to have the effect of taking orbits. So if the trace map M1, if this is an isomorphism, which is equivalent to saying that M is the orbit Mackey functor of M0. Yeah, in the actual examples, we'll deal with a trivial action, but for general purposes, it's illuminating to use. So really, there's a Bay action here. Okay, so if this is satisfied, then that means the homology here is going to be 0. So our homology, the bottom row is exact, so our homology is going to be 0. No, 0, or sorry, this one isn't. Our homology here is going to be 0, so, then trace is surjective. So we'll also get zeros here. And then here we'll get the kernel of 1 minus gamma, so that's the fixed points. And then going like this, and then again, the fixed points of M0 CP is M0. So I get inclusion and trace. So these, we're wondering like how you're supposed to think about like an ROG graded suspension of a Mackey functor. That seems very, very abstract. If we take a Mackey functor, oops, if we take an orbit Mackey functor and we suspend that by this lambda minus 2 representation, which on the underlying is an equivalence, then we get the fixed point Mackey functor for the same G module. So these ROG graded representations are doing sort of controlling restrictions and transfers, and they let you give lots of different descriptions of Mackey functors. I'm not sure what a general, it would be very interesting to study in general, like this sort of action of the, I guess the action of the augmentation ideal, so virtual representations of virtual dimension 0, and how they're acting on subcategories of Mackey functors or of G spectra. In particular, so this was just an example for CP, I stated my result in terms of this representation of the width vectors Mackey functor, and then make all of the restriction maps above Cn, where again, this really means this injective. But this is the same as the lambda n lambda suspension of, if I take instead the sub-Mackey functor of the width vectors Mackey functor generated under transfers by the restriction here. Because again, the difference between these is we're suspending by lambda 0, or lambda, sorry. Yeah, we're suspending, we're taking away the trivial representation, adding this lambda n to go from here to here. So there isn't necessarily a like best way to write one of these suspensions. Now, if you want to do, say we want to do an example for CP squared. So when we smash these together, so we can build so we have cell structures for these S lambda J's, for any alpha in RUT, by smashing together these cell structures for the S lambda J's. Now, when you're doing this, you need to be careful. So let's say I is less than J. We look at like S lambda J, S lambda J smash T over CP to the I plus, or S lambda I smash T over CP to the J plus. So if you just think about like I being 0, so the trivial the trivial subgroup, and then so if we so like S lambda 1, if you restrict that to the same, one of these will end up being the same as just the corresponding unequivariant sphere. So if when you smash with S2, smash this. I think I want yeah, so if we took, for example, S lambda 1, so this is Z is acting by Z to the P, then this would be trivial for zeta P. Sorry, I'm not good at thinking on the spot. What I want to say is you have to, when you're doing these cell structures, what you want to do is smash these in the, go in descending order to make sure that you still end up with trivial spheres so that you can get something you can compute. So explicitly, if we took M a CP squared Mackey functor, and let's say we wanted to compute pi star of minus lambda 0 minus lambda 1 of M. So in other words, the homology of S lambda 0 plus lambda 1 with coefficients in M, then we would have M0 CP squared over CP, M0 CP squared, and then that thing again. And then, so this is in degrees 4, 3, 2, 1, 0. Then here we would have M1 CP squared over CP. And then down here we would have M0 CP squared over CP. Then this thing again. And then here M2, M1, and M0 are original Mackey functor. So then you can calculate the homology of this very explicitly. And for instance, you could see something similar for like what happens when you suspend by something like lambda 0 minus 2 or lambda 1 minus 2 or lambda 1 minus lambda 0. So I think that's what I wanted to say about how to compute with these cell structures. One other comment to make is that, I'll erase. other important comment to make is that, so as CN spectra, these have these two-stage cell structures, but as S1 spectra, these have one-stage cell structures. Namely, we have a cofiber sequence like so. So if you're working at the level of S1 fixed points, because it's very easy to, it's even easier to work out what these ROG graded groups are. Okay. Now I want to go back into presentation mode. Is this still, can you see my screen still?
Yep, we can still see your handwritten screen.
Great. Okay, so now I want to give our ansatz for our guess for what the slice filtration should be. So let X be a G spectrum whose underlying is polynomial on a degree 2 generator. This means the Whitehead tower of the underlying is just given by even suspensions of X. So our guess for the slice filtration should be maybe, hopefully it's just some ROG graded suspensions of X where the complex dimension of the n is n, and these are connected by some RUT graded classes, which reduce to this thing here. So I'm giving this right now at just sort of a level of generality of G spectra. I haven't done this yet, but I suspect you could axiomatize this argument and prove it for both like THH and Almond's example of KU simultaneously. You could probably say something even more general. Well, fortunately, okay, so what we need, just using that Hill-Yarnell characterization, we need the connectivity of these geometric fixed points to be at least this number. Well, geometric fixed points is monoidal, so we can just pull that out. And so we get then, and then on suspension spectra, it's just going to be the sphere, the representation sphere of the fixed points of the representation. So if we suppose that our geometric fixed points are all connective, then all we need to guarantee, in order to guarantee that this is slice 2n connective, is to find some representation such that the real dimension of the fixed points is greater than equal this. Well, as luck would have it, we've already seen a representation that works here. We've found the complex dimension of the fixed points is the ceiling, and then that just sort of works out with the two. So that's very convenient. But even if we didn't, if we hadn't had the foresight to think of this in advance, this would have been forced on us. Originally, that's sort of how I found it. So as an example, so here's an example with P is 3. So here's all the connectivities that we would need. Now, if there's a 1 in all the columns to the right, because we're taking ceiling, that means we have to include a trivial representation to get at least that connectivity. Okay, so in all cases, we're going to have a trivial representation. Notice here that this is giving us like more connectivity than we need, because we just need to be at least 1. So here we've gotten up to 2, so this one is done. Now here we want connectivity. So here the connectivity is 2 for these two, which is correct. But we want to add some connectivity to the underlying without changing the connectivity of the fixed points. Later we will, to do that, we will add a lambda 0. So if we're doing it in this order, we would, if we're doing all of them at once, we see, okay, these ones are good in this column. Now to increase the CP fixed points, or CP connectivity and the underlying connectivity, that is where we add the lambda 1. So lambda 1 will increase, yeah, the underlying connectivity and the CP fixed points, but nothing else. And then these lambda zeros will only affect this column. So at least the p-typical decomposition was forced on us. And then you can sort of notice after the fact that these are the p-typical decompositions precisely of this representation. Right. So, so to prove our guess that this is the slice filtration, we'll need to show that the suspensions are greater than or equal to 2n, which we've just done. Then we'll need to produce some maps between those. So we've already done that. We'll need to show the cofibers of this map are then slice less than or equal to n and slice greater than or equal to 2n. Now, for this, so in our case, the cofiber is going to be this ROG graded suspension of a Mackey functor. And so something that proved that will be useful for generalizing this argument to G spectra is, in fact, if T is any, or if M is any S1 Mackey functor, then the suspension is slice less than or equal to 2n. So that step is already done. All right, so now I'll specialize to talking about THH. Dan, how much time do I have? I can't see the clock.
About 5 minutes left.
Okay. Well, so go through this very quickly. Setup A is a p-torsion-free ring. We have a ring isomorphism lifting the Frobenius. There's a non-zero divisor. We're interested in the THH of R. There's a crucial property that phi of this thing is congruent to P mod this thing. I'll explain why that's important. I set this thing PNA to be the product of all of these with the appropriate Frobenius applied. So also PA is just this psi. And then we have an isomorphism from the width vectors of R to this A mod PNA. This is compatible not with the restriction maps, but the Frobenius maps on the width vectors. And again, if you don't like perfectoid, you can just take A to be ZP, phi the identity. These are just the ordinary P to the n's, and R is FP. So that connection, that congruence is important because so the width vectors, we said these mod things end up being the same as the width vectors. In the width vectors, we have to have an axiom that F followed by V is congruent to P. Here, the transfer V is given by multiplying by phi of this thing. So some connections between equivariant homotopian arithmetic geometry. This prism condition, as it's called, is basically a special case of this axiom for Mackey functors that trace restriction, or that should say restriction of trace is the sum over conjugates, which in the case of a trivial action is just times P. The decomposition of this representation is related to, as I said, the Legendre formula and the Q'd analog of this. There's also norm maps in equivariant homotopy theory coming from these sort of multiplicative aspects of equivariant homotopy theory. And these, quite interestingly, turn out to be lifts of what the arithmetic geometers call Q-twisted powers. And in fact, so these expressions lift this expression. On the other hand, if you start out with this thing, then the fact that this descends to a map from the width vectors turns out to actually be equivalent to what you might call the fundamental lemma of Q-crystalline cohomology, which is pretty cool. And then the fact that the norm scales slice filtration, this is a universal property of the slice filtration, is closely related to a lemma that goes into the convergence of the Q logarithm, and is probably useful for other things. So these are some of the connections I'm trying to explore and see what this is useful for arithmetically. So I think I'll skip through that. I just want to talk about, so we can use these cell structures to get the ROG graded THH that we're after, but want to put that computation, make it more conceptual and more multiplicative. So if V is a G representation, then the inclusion of the zero subspace gives us a map from S0 to SV. And we view that as a class in pi G negative V of the sphere. Now this is trivial if and only if V has fixed points, because if V has fixed points, then we can homotope the inclusion through a fixed point, through the suspension of a fixed point subspace. And so therefore, AV kills transfers from the stabilizer subgroup for V and is killed by restriction to that subgroup. So this controls transfers and restrictions again. So that cell structure, the S0 to SV is this A. In particular, S infinity lambda 0 is a model for this classifying space. So you can think of the isotropy separation square as an arithmetic square for this Euler class, this equivariant Euler class. There's another source of equivariant class, ROG graded classes, coming from what are called Tom classes. So the Borel homotopy only depends on the coarse equivariance. So what we get is these invertible classes living in like underlying degree 0, but ROG graded degree this. So it lets us swap ROG graded like representations for trivial representations when we're looking at Borel G spectra. So in the isotropy separation square, all of these have this U lambda periodicity, and this column has this A lambda 0 periodicity. So we can use this periodicity to bootstrap from the Z graded case, and then this column to induct. All we need is what's the relation between these two generators. So in Hill-Hopkins-Ravenel, they have a relation they call the gold relation because of A and U, that A lambda J, U lambda I, when I is less than equal J, is P to the J minus I. So that doesn't help us here because we're not looking at underlying Z modules. What we'll do instead is the following. So Silitus's theorem tells us that for this representation, the TF homotopy will actually be isomorphic to the TC minus 1. So this is the Borel one, which then by the periodicity is the same as just you write the degree 2 generator and then move that into ROG grading degrees. So Silitus's theorem is sort of a form of the Siegel conjecture. So again, if you're generalizing this to general G spectra, you'd be looking for some version of the Siegel conjecture. On the other hand, the cell structure that we have for T spectra gives us that A lambda I is the kernel of the restriction to TRI plus 1. And so that gives us a relation between these. Sigma times A lambda I is this PI plus 1 U lambda I, which you can write in various different ways. So I call this the Q-gold relation. Interestingly, you can combine these two forms of the Q-gold relation if you formally set A lambda negative 1 to mean 1 and U lambda negative 1 to be the Bachstadt generator. So that's sort of a philosophical interpretation of what the Bachstadt generator is doing. It's sort of like a Tom class for a representation that doesn't exist. So once you have this, you can compute the entire, this reduces the problem of computing the ROG graded homotopy of THH to something algebraic. So I'll advertise that in upcoming work, which will hopefully be out soon, I compute the entire ROG graded, ROS1 graded ring TF. Okay. So yeah, just cut me off when it's time to stop, I guess. So we want to produce some maps between
I would
these.
just go ahead and just wrap it up now. I mean, just, finish what you're saying and then wrap it up.
Yeah, so we want to produce some maps like this. We can pull this out and just reduce to looking at like some single degree. So we claim that this is what we have. So these blue classes are again given by Silitus's theorem, so the sort of the Siegel conjecture. And then the cell structures tell us that we have here is generated by traces. Skip this. So since we've got this stuff is multiplied by sigma, and then here we have just a Mackey functor. So that gives us, we isolate a Mackey functor. We get this. The reason that the connectivity works out is we take phi CP here. So here we won't get the necessary connectivity from the sphere, but here that we're looking at the sub-Mackey functor generated by transfers, that gets killed by geometric fixed points. So that's how we get the necessary connectivity. And I'll finish. These are just some charts of the ROG graded homotopy of THH. So one important thing is that in general, you do expect to have junk in the negative odd degrees, but you don't in degree -1. So there's a gap phenomenon there that was essential to be able to isolate just a single Mackey functor in here. So this is where we got that single Mackey functor. The other reason, oh, and so yeah, this looks slightly different depending on whether you're over FP algebra or perfectoid ring. Then the reason that I used the long cell structure for this theorem is that that junk in odd degrees doesn't appear at the level of TF. So you have to work a bit harder if you want to use the easy cell structure and then transfer it down to this finite level. I think I'll stop there.
Okay, great. Thanks very much, Yuri. Hang on a second. I'm gonna